Okay, then, welcome. I welcome you to the first week on and the first problem solving session of the course Introduction to Fluid Mechanics, which is taken by our Professor Suman Chakraborty from IIT Kharagpur. And uh, this will be a session completely dedicated to discuss similar problem that has been asked in the assignments of the course, and students are most welcome to clarify their doubts regarding the assignments. And again, I would like to just say beforehand that okay, so just I would just like to inform beforehand that this session will not be entertaining any questions regarding the solutions of the explicit solutions of the assignment that has been asked in the questions of the assignments that has been asked to be solved by the students themselves. So students are requested not to ask for the direct solution of the questions that has been asked in the assignments. So we will try our best to help the students out by solving similar kind of problems, so that that could aid the students to solve the problems that are given in the assignments. Okay, so I guess I'll wait for few more minutes, hoping that some students may join, and then we can just get ahead with the session, I guess. So okay. Okay, then I feel that I guess we can start the session today. So uh, given that it's the first week, so I guess we have uh, Professor Chakraborty might have discussed briefly about the overview of the course, and moreover, would have definitely covered the simpler concepts or simpler beginners concept related to fluid mechanics. And even though it may seem quite what to say uh, easy or simple in the beginning, but I would suggest or request that students emphasize on the uh, emphasize on this fundamental nature of these concepts and try to build upon these fundamental concepts for the rest of the course. So that would be a better way to approach the course. So even though these topics are very simple, but these are the fundamentals upon which and the entire course will be based upon. So it's necessary that our fundamentals are clear. So to begin with, since very few students have joined, and given this is the first session, so I don't think there will be much time needed. Uh, I would be taking this. What I meant is that I will not take this session for a longer period of time. So I'll try to keep this session as short as possible because many students have not joined. So, uh, so to begin with, uh, Professor Chakraborty discusses the topic of. Let me go back to the notes. I guess that would be better. Okay. Yes. Uh, so here you can see that uh, that in the for the beginning, uh, Professor Chakraborty has discussed about the concept of continuum hypothesis, and it continuum hypothesis basically helps us to consider the fluid as a continuum, because if we look closely or dive deep into the physics of the fluid flow, we can consider fluid to be comprised of various fluid particles. Fluid particles basically implies to a accumulation of certain molecules of fluid molecules that would uh, comprise a particle that is small enough to mitigate the errors that may arise because of its largeness. I mean, if the fluid particle is much larger than uh, the fluid particle that we have chosen for our calculations, say the calculation of uh, density, calculation of intrinsic properties such as sorry, calculation of uh, intensive properties such as density, that mass per unit volume. So this size of the fluid particles should be small enough so that the errors related to this measurement of densities is mitigated, and also the size of the particles of these fluid particles will be large enough so that the uh, the continuum hypothesis is satisfied. I mean, like if the fluid particles are very small, the errors that might incur because of the measurements of the uh, fluid properties may very uh, significant. Like at a particular instant, if we have a very small fluid particle, if at a particular instant we measure the fluid property, it may give some certain values. At the different instant, if we measure the same fluid property, say even in the same experimental conditions, it will give a different result. So these fluctuations in the results can be mitigated if we choose the fluid particle to be large enough so that the continuum hypothesis is satisfied. So given that basic overview about continuum hypothesis, so a, a parameter or a value that gives us a quantitative understanding of continuum hypothesis is the Knudsen number, which is let me go there, which is defined as the ratio of the mean free path of the fluid particle to the characteristic length scale of the flow. Okay, so the mean free path or the molecular mean free path, as it is mentioned here, basically refers to the average distance that a fluid molecule will travel before encountering a collision, and the characteristic length scale, it is the length scale of the flow that governs the flow properties such as velocity and pressure. It basically what I'm trying to imply here is that the characteristic length scale could be defined as a length scale along which there is a considerable change in the velocity of the flow. Since velocity is okay, okay. So welcome to the problem solving session for the introduction to the fluid mechanics course. So it seems that we already started the session, but we have not dived deep into the session, so it's just the beginning. So you are welcome to join now. So as a general protocol, we'll briefly discuss about some of the topics that has been discussed in the first week's session, and then we will directly dive to the some questions and answers that will help you to solve the problems in the for the first week of the course for the first week assignment. So I hope that's clear. So here we were discussing about the Knudsen number. So I see here, let me check it. I see here that Aniket has joined the session. So, Aniket, if I'm audible, could you please?
Yes, sir.
Okay, thank you. So, if I'm audible, could you please define me what? I guess you have attended the first week session, right? The first week lectures.
No, actually, I didn't attend all the lectures. I'm
Oh,
just here for the course overview.
okay. Actually, Aniket, the thing is that the course overview has been briefly described or very properly described by Professor Chakraborty in the uh, first week lectures. So I would suggest that you look into that. But since this is a first week session, I don't think there's much. It will not be that quite heavy for you to grasp it. So I guess it's much simpler for the first week session at least. So I welcome
Okay,
you to
sir.
join the session. But still, uh, did you attend any fluid mechanics course in your like undergraduate or whichever platform you're studying right now?
Yeah, I attended some basic lectures.
Oh, sure. Then I guess then you might have heard about the Nutsem number. It's a non-dimensional number, I guess. Yes.
No, I think I didn't
Okay.
till now.
Okay, that's completely fine. Okay, so here we are discussing about Nutsem number. So see, the content of the first week is or the first week lectures are very small. So we'll just dive into bit of the concepts, then directly go to the question and answer. That will help you to understand the concepts even better. Okay. So
Okay.
here, Knudsen number is basically a non-dimensional number. So in fluid mechanics, if you're reading or if you are going to read in the later part of your academic life, non-dimensional numbers play a very vital role in determining various uh, or quantifying various flow properties in a fluid flow that would help us to understand the basic nature of the flow. For example, there are various scenarios where the scale of the problems may change from experiments to experiments, or if you're doing analytical studies, the scale of the experiment may change from, say, a microscopic analysis, for example, the fluid flow around a bacteria. That can also be a flow problem, and the fluid flow in a large dams that can be different problem. So these scales, this variation in the scales are so large that uh, to have a to have a uniform understanding of the problem, researchers have devised non-dimensional founder governing equations which give rise to certain non-dimensional numbers. So I will give you an example. For example, when you are dealing with experimental analysis such as flow over an aircraft, and if you want to uh, model that uh, flow, so what happens is that you want to carry on that experiment in a uh, uh, laboratory. So you cannot, it's very difficult to do that large scale experiment in a uh, do that it is very difficult to replicate the entire large scale experiment in the laboratory, right? It's very difficult to create that aircraft uh, of similar size that we usually use for traveling. That large scale plane, the large scale plane couldn't be designed or replicated in the laboratory conditions. So what researchers researchers actually do is that they create a smaller scale model, and that use those use those models to understand the flow physics of the flow over an aircraft. But since the flow physics or scenario has been changed because of the very change in the scale of the experiment, that's why the equations that govern the flow physics should also have to be changed accordingly to take into account this difference in the scale of the experiment or the flow analysis. And that's why, in order to incorporate the differences in the scale of the experiment, but given that the flow physics that we're trying to study is the same, people use uh, non-dimensional form of the governing equations which give rise to these non-dimensional numbers, and one of those non-dimensional number is the Knudsen number. So Knudsen number basically helps us to quantify the continuum hypothesis that Professor Chakraborty would have discussed in the lectures, right? So, as I've already mentioned, that Nusselt number is basically the ratio of the molecular mean free path of the particle and the characteristic length scale of the particle. And if the value of this Nusselt number is much lesser than 1, then the continuum hypothesis is valid. Okay, but if this Nusselt number is much larger than 1, then it basically implies a very rarefied system. Rarefied system basically means that the fluid particles are at a much larger distance in the characteristic length scale of our study. And in that scenario, the continuum hypothesis is no more valid, and the governing equations that we use for our analysis have to be modified accordingly so that we could incorporate these rarefied systems. Okay. So, I guess that's all for the this continuum hypothesis and the Nusselt number. Then we look into a very interesting terminology that has been discussed by Professor Gupta. Sorry, Professor Chakraborty. Uh, and that is the concept of traction vector. Okay, so I guess I won't dive deep into the analysis and the derivation of traction vector. So I will just give you a definition and uh, hope that you are able to grasp it. But if you have any doubt, you can ask me within this our discussions, and if I'm not able to clear it, you are most welcome to go to the lectures so that your doubts are properly clarified. Okay, so traction vector is basically a way to uh, quantify the stress components, stress vector, stress tensor components that act in a particular direction. Okay, so I know it's difficult to understand by the very definition, but what I'm trying to basically imply is that we know that the stress tensor is a for a for a Cartesian coordinate system, or in a 3D in a 3D analysis, the stress vector is a 3 cross 3 matrix, right? It has 9 components. So what traction vector basically does is that, say if we want to have a traction vector along a particular direction, then what traction vector does is that it clumps up or clumps up all the distance, all the components of the stress tensor that uh, contribute to the force in that particular chosen direction of the traction vector. Okay, so I guess I can directly go to the notes now. So here, if we look into this, if we look into this definition of the traction vector that has been discussed in the lectures. So, uh, so here I denotes the direction of the traction vector along which we want to find a traction vector, and J denotes the components of J will denote the corresponding components of the uh, stress tensor that is contributing to the traction vector in that particular direction. Okay, so and this very definition of traction vector is also known as the Cauchy's theorem, as recently discussed by Professor Chakraborty. Okay, so now I feel that we have discussed enough, and it will wise enough for us to directly go to the problems so that it could help you to understand the concepts even better. Okay, so let us directly go to the problems. Okay, so the first question is, which among the following statements is or are regarding is or correct regarding the continuum hypothesis? Okay, so these are your options. So I believe I will give you some time to look into the options and then just tell me the answer if you know, and otherwise we are going to discuss it anyway. Okay, Okay, then. So the correct answers for this question would be uh, both. Let me just tick mark it. B as well as C. Why? Because as we have discussed briefly in today's session, that continuum hypothesis is applicable for macroscopic approach, in the sense that given that the particles are not that large, so that would incur additional errors while measuring the fluid properties, right? So the particles should be small enough, but not that small that it will again lead to fluctuations in the measurement of those fluid properties when we measure it at different instance of time. Okay, so that is also very important. Okay, so that's why it is very from microscopic approach. We are disregarding this microscopic part because we do not know what does this statement actually is trying to imply, like whether the free particles are very small or whether it is going to uh, whether it is going to discuss about the analysis up to the fluid molecular level. So it is not specifying that explicitly, and moreover uh, the very uh, conceptualization of the macros of the continuum hypothesis is for the macroscopic analysis of the fluid flows. That's why this is uh, more apt for this particular situation. And secondly, option C is correct because it basically is implying to the definition of the continuum hypothesis, that in the case of continuum hypothesis, the fluid can be regarded as a continuous medium disregarding the discontinuities. Okay, and this discontinuities may arise if we even scale down even further. If we go back to the molecular level, there can be some discontinuities which in turn lead to the fluctuations in our measurements, and that's why we don't want to go down to that small scales. That's why to mitigate those errors we choose a certain size of a fluid particle that satisfies the continuum hypothesis and is would be valid for the further analysis of the fluid properties. Okay, then let's go to the second question, that which among the following expressions is correct regarding the Knudsen number. Okay, so I guess we have discussed about it in depth in our discussions today, so it's very simple, I guess. So here option A would be the correct answer. Okay, then let's go to the next question. So here it is asking that which among the following statements is or are correct regarding the Lagrangian and the Eulerian approach? Okay, so at this moment, I guess I can, since the question is arise, so I guess I can take some time to discuss about the Eulerian and the Lagrangian approach. But again, students are most welcome to give your answers. But still, uh, I would like to discuss a bit about the Lagrangian and Eulerian approach. Okay. So in this case, the correct answers would be A. In the case of Lagrangian approach, we track individual fluid particles first, and secondly, the option D. In the case of Eulerian approach, we focus on a specified region. That would also be correct. So these are basically definition. These are basically the definitions of the Lagrangian and the Eulerian approach. But still, I guess we can discuss about these a bit. Okay. So as it is mentioned here, that in Lagrangian approach we track individual fluid particles. Okay, so what it is basically trying to imply is that in the case of this, both Lagrangian and the Eulerian approach are two different methods to study a fluid flow system. Okay, so in the case of Lagrangian approach, it is basically the control system approach. By control system, I mean is that the system of the fluid flow that we are going to study, it is fixed and it has it is of fixed mass and of fixed identity. Okay, this term that of fixed identity is very important. Why in the sense that throughout our analysis, the identity of the fluid particle or even the system that we are going to study remains constant or remains same. So what basically happens is that in the case of Lagrangian approach, we say if there's a uh, system that we're going to study that is comprised of say n number of particles. Okay, so these particles are free to move around and travel within the system, within the system that we're going to analyze, or if the system is moving, that is free to move along with the system. Okay, and the particles, they themselves are can be considered as systems, or in the case, since there are n particles, so we can consider there are n systems that we're going to study. Okay, and the motion of these n number of particles would impart certain force on the, say, on a particular geometry upon which we are going to study the effect of the fluid flow. So this n number of particles would impart forces on the geometry that has to be that we want to study, right? So in the case of Lagrangian approach, we would track each and the motion of each and every particle, each and every of these n particles, and see how these particles move in the space, and how the motion of these particles are modified because of the external forces that may act upon these fluid particles, and how these particles then impart the force on a geometry that we are concerned about, how this each and every particle impart their force on this particular geometry, and how the fluid flow is then modified. Okay, so this is basically a Lagrangian approach. There is no flaws in the analytical approach of the Lagrangian approach, that there is no analytical flaw or discrepancy in the Lagrangian approach, but the basic uh, difficulty in uh, undertaking Lagrangian approach of a fluid flow system, Lagrangian approach for the study of a fluid flow system, is that it's very computationally expensive. Okay, uh, like I myself am a researcher who is uh, predominantly working on particle tracking, so I know that tracking this computational cost of tracking certain number of particles, if it goes beyond a certain value, then the computational cost uh, increases rapidly or exponentially. So it's a very computationally heavy uh, method to understand a fluid flow system. Okay, that's the major flaw of the Lagrangian approach, and that's why in order to uh, uh, tackle this computational expense, the Eulerian approach was devised, that is being given in option number D, that that instead of following each and every particle in the system, now we focus on a specified region. Okay, so I guess it would be much better if we described it with the help of a diagram. Okay, so consider that we have a particular box. Okay, let's say we have a particular box, that is our geometry. Okay, let's consider two identical boxes. That would be, okay, size is different, but I hope you understand that just they are just identical boxes. Okay, so as I mentioned, in the case of Lagrangian approach, what happens is that, say there is a flow of fluid inside this control, inside this box. Okay, let me not use the specific terms right now, because that has not been that have not been mentioned yet. And there is an outlet. Okay, okay, so okay, here again you can apply the continuum hypothesis by the means that these are not different streams of fluid flow, but rather is a continuous stream of fluid flow. Okay, these arrows are just giving the direction of the fluid flow that we're going to analyze. And this stream of fluid, let me just name them as inlet and outlet. Okay, inlet and outlet. Okay, so this stream of fluid would have n number of particles along this stream of fluid will be comprised of n number of particles, right? So say let me just use different color, say I'm using green. So there will be n number of particles that will come along with this stream of fluid, and these particles then would go around with random motions, right? Basically because of the confinement, right? This box is, this box you can consider as a hollow duct. So this duct would uh, provide a confinement to the stream of the fluid, and since this is a solid boundary, these particles would now go and collide with the surface of the, with the walls of this duct, then jump back to the fluid, jump back inside the stream again, and then these particles may collide with other particles, uh, and then again the direction of those particles may get changed because of this collision, and then this would be the basic trajectory of the, of a particular particle. If I zoom in, this would be a basic trajectory of a particular particle. Then after that this particle will go out, and similar case for all other particles. Okay, and then it will again go out as a single stream from the outlet. Okay, so what the Lagrangian approach basically does is that in order to analyze this fluid flow from the Lagrangian point of view, we have to track the motion of this particular fluid particle throughout the throughout the length of this duct. Okay, we'll see how this collision has occurred, then how the collision of this fluid particle with the wall of the duct has imparted certain momentum to this fluid particle, then how this fluid particle when colliding with a different fluid particle, say, has again changed its direction because of this collision. So we need to take into account all these calculations throughout its trajectory for a single particle. It's a single particle that we're considering right now, and there can be again n number of calculations that we have to do to determine its trajectory. Okay, and once we know the trajectory, we know its velocity, and once the velocity is known, we can determine the acceleration, and then thus the force that is being imparted by the fluid particle on the duct or any system that we are going to study, right? That can be done, but these are the number of calculations that need to be, that has to be considered while computing the trajectory of a single particle, and similar analysis can be done for n number of particles in this case. Okay, now, and I guess it's quite clear or quite obvious why this approach is generally not considered to be suitable for basic fluid flow analysis. Okay, you don't want to scare any budding researcher by giving them such problems. They will just leave the field of fluid mechanics if they get to know that this is the only approach that is available for understanding the fluid flow systems. Okay, and thus in order to counter this uh, problem, fluid researchers or fluid mechanics experts have devised another approach to study fluid mechanics, fluid flow problems. Okay, and that is known as the Eulerian approach. I'll just write it here. Eulerian approach, and this is the Lagrangian approach. Let me just name them so that it would be helpful. Okay, Lagrangian approach. Okay, so in the case of Eulerian approach, we consider the same system or same geometry. Then again there is an incoming jet of fluid flow, of incoming stream of fluid. That would be a much simpler explanation to the condition. So again there's an outlet of outlet stream of fluid that we are considering. Just let me just name them. Inlet and outlet. So in the case of an Eulerian approach, rather than focusing on a single particle or the same identity of the system, we are now more interested on a particular specified region. So even though the mass within the control or the mass within the system that we are considering may remain constant, but our identity changes because of the flow of the fluid, right? Since the fluid is flowing past this particular duct or system that we are considering right now, the identity of the fluid flow is changing because we are not now not concerned about the particular number of particles or certain number of particles, but rather we are now primarily concerned on a particular region or specified region of the flow that we can say specify by certain dotted lines. We are now more interested in this particular region rather than each and every particle of the fluid, right? So we are now concerned what happens to this particular region rather than the uh, n number of fluid particles that we were following in the Lagrangian approach. Okay, so what would happen is that in the case of Eulerian approach, the flow would this flow of fluid to this particular system or duct would impart certain force on the duct or the particular geometry. Okay, and rather than focusing what happens within this system, we are more concerned on what is the flow property at the inlet and the outlet. And as you will eventually see when we discuss about say Reynolds transport theorem or the control volume approach of fluid flow analysis, we'll see that it is the property or the parameters of the flow at the inlet and the outlet. Okay, we are not concerned what is happening inside this uh, particular system. That's why we consider this as a black box. Okay, we do not know what's happening inside, but what's important or necessary for us to know is what's happening at the inlet and the outlet. And the flow parameter that we are primarily concerned in the case of Eulerian approach is the velocity profile. Okay, so if we know the velocity profile at the inlet and the outlet, we could determine the net force that acts on this particular duct or geometry because of this fluid flow. Okay, rather than calculating the momentum imparted by each and every particle in the case of the Lagrangian approach, we are just concerned with the net force that we can evaluate by knowing the velocity profile of the fluid flow at the inlet and at the outlet. This I'm not going to discuss now thoroughly. I guess it would be better if we build up our concepts from now on. It is just for your understanding that these are two different approaches, and we'll eventually get a broader understanding when we discuss the Reynolds transport theorem and how the governing equations for the Lagrangian approach are transformed to Eulerian approach by using the Reynolds transport theorem or the RTT. Okay, so that's what I wanted to say for right now. You just know there are two different approaches, how they're different, and why these two different approaches exist. Okay, so let's go to the next question. I guess it's question number 4. Okay, so the question is, which among the following is the correct mathematical form of the angular momentum principle for a fluid flow in the absence of any body couples? Okay, so I think this is quite uh, explicitly phrased. This question is quite explicitly phrased, and I think this topic has been very thoroughly discussed by Professor Chakraborty in his lectures. So I don't think I will go back to derivations. I had the derivations, but I don't think I will go back to it again. So I would emphasize that students go to the derivations. If they do not remember, they can go back to derivations and see what are the assumptions that he has taken to get into the final form of this particular statement, and what are the necessary conditions that need to be satisfied so that this equation is valid. Okay, so I guess the answer, all of you know the answer. So the answer would be option number C, that tau ij is equal to tau ji. Okay. So, and this statement is also, I guess, if you have taken any solid mechanics class course such as strength of materials, this statement is also being told as the principle of complementary shear stresses. Okay, I suggest that you can go back and look into it. But even though the platform of analysis, that is basically in that case we are discussing about solids, but in this case, in our case, we are discussing about fluids, but the concept remains the same. Okay. But still, I will emphasize, I will request that you go back to the derivation for this this equation in the lectures. So that will be very handy for you to see how we have that are reached to this conclusion. Okay. Okay. The next question is, determine the number of independent stress tensor components tau ij in the absence of any body couples. Okay. So as I was mentioning the necessary conditions, that one of the necessary conditions is in the absence of any body couples. Okay. Absence of any body couples. It's a very important condition that needs to be satisfied so that this equation is valid. Okay. Let me just highlight it. Okay. So the next statement, the next question basically is in, I guess it's a continuation of the previous question, question number 4. So it is saying that what is the number of independent stress tensor components in the absence of any body couples. Okay, so it is saying that this condition is already satisfied. Okay, so but it basically means is that tau ij is equal to tau ji. Okay, so to answer it, I guess it's very simple, all of you will know it, but let's just uh, write the stress tensor and its components so that it's quite obvious once I draw it. Okay, once I write it, I'm sorry. Okay, so if tau ij denotes the stress tensor where I could vary from 1 to 3, we are discussing in a 3D case, and j would vary from 1 to 3. Okay, and there is a very important what to say, significance of this particular indices. Okay, then what this particular indices imply. Okay, so the first in the index basically indicates the plane of application of the stress and or what I can say is that the plane perpendicular to the direction of the application of stress, that would be much that would be much proper definition, but that will be more appropriate definition for this particular index, sorry. So it could be, it is basically the plane perpendicular to the direction of the application of stress, and j denotes the direction of the direction of the component of the stress we are trying to evaluate. Okay, component stress, we just write up to that. Okay, so if I go back to the diagram, I guess if I go back to the diagram here, yes, okay, so you can see here that if tau 11 is the particular stress component that we're discussing right now, so first index denotes the direction normal of the surface, basically direction of the particular plane that is perpendicular to the direction of which direction of the stress component that we're trying to evaluate, and the second index denotes the direction of the I'm sorry, direction of the action of the force component. Okay, so let me just take an arbitrary plane right now. Okay, let me just take this plane. I take this plane, okay, and then just denote the stress components, say this and this. Okay, I hope it is clearly visible now. So if say these are the three different stress components right now, so the first component here, since it is this direction is perpendicular to the direction that this direction that we are going to analyze is perpendicular to this particular plane, and this plane would be the this plane is perpendicular to the y-axis, right? So if y denotes the y is denoted by the index 2, then this would be the first index in this case would be 2, and sorry, and since direction of the force or the stress component is along this along the y direction, so the second index will also be 2. Okay, similarly this component, for this component, the indices for the stress would be tau 2, because the plane above upon which the stress is acting has not changed, so it will remain 2. Since the direction along which we are trying to evaluate the stress component or the force, corresponding force because of the stress component, it has changed, so it will become 1 because it's along the x direction. Similarly, this component would be, again, the first index will remain 2 because the plane has plane is the same, and since the direction is now along the positive z direction, so it would be that the second index would be 3. Okay, so this is the basic what to say, sign convention or notation that is used to determine different components of the stress tensor. Okay, so now if we are now trying to say write the stress tensor, so tau ij, say, could be written as tau 11, tau 12, tau 13, tau 21, tau 22, tau 23, tau 31, tau 32, tau 33. Okay, and since this statement, this condition is satisfied, so this would, I'm sorry, so this would imply that tau 12 is equal to tau 21, right? Tau 23 is equal to tau 32, and tau 31 is equal to tau 13, right? So let me just use different colors, say. So these two are same, this and this are same, and these two are same. So if we consider this as three different elements, so this will comprise of three elements, components, and the remaining components are the normal components of the shear stress tensor, that is tau 11, tau 22, and tau 33. So 3 plus 3, so it will tell that there are 6 independent stress tensor components in the absence of any body couples. So the right answer would be 6. Okay, so I hope it's clear up to this point, so we can go to the next questions right now. Okay, So this question is again, I guess, quite pretty straightforward. So here it is asking that consider a differentially small triangular wedge-shaped fluid element as shown in the figure. Here P1, P2 and P3 are pressures acting on the three surfaces. It is P1, P2 and P3 are the pressures acting on the three surfaces. Let Bi be the component of the body force per unit volume in the ith direction. Okay. Then which among the following is correct for the force balance along the x direction? Okay. So I guess this question is pretty straightforward, and Professor Chakraborty has extensively discussed this particular geometry and has derived a particular law that we will know as the Pascal's law. So he has done a extensive analysis of this particular elemental form of this fluid element, say. So I don't think I need to go back and derive the entire expression once again, but here they have not even asked the entire derivation. They have just asked the force balance along the x direction, and similarly the next is along the y direction. So they have just asked the force balance along the x direction and the y direction. Okay, so we'll just do the force balance. So after doing that, we will see that the force balance the force balance gives the conclusion that along the x direction the force balance would give us the conclusion P1 equal to P3, and along the y direction it will give us P2 is equal to P3. Okay, that will basically then lead us to the final conclusion that P1 is equal to P2 is equal to P3 for a very small elemental uh, fluid, very small differential fluid element. Okay, so there's a final conclusion. But still, if you still have any doubt regarding the derivation, I will again, let's just go back to the uh, derivation that we have done. So hope it is here. Okay, it's not here, then yes. So for question number 6, so let me just do it there. I guess that will be much simpler. Or okay, then if you just look it, I will just do along the x direction, and the y direction you can do accordingly. So along the x direction, then if we consider they've told that the length of the is this wedge shaped part is dl. So considering that, then it tells us that dy would be equal to dl cos theta. Okay, from this expression, from this given this angle is theta, so we can write that dy is equal to dl cos theta. Okay, so the net force along the x direction because of pressure P1 would be P1 dl cos theta, right? Then the only component of force that's remaining to be balanced in the x direction would be the force along the x direction due to the pressure P3, right? Which would be again P3 cos theta, that is it's right. Basically we decompose the uh, see again I guess this is conceptually wrong to write like this, so let me just not do it in this way. Okay, so it would create further confusion. Okay, so it is the force that we decompose and not the pressure, right? So rather I will write it in this manner. Okay, so the net force on this wedge shaped element would be P3 dl. Okay, so let me just write it. It is P3 dl. Okay, the net force is P3 dl. So the component of force along the x direction would be now P3 dl cos theta, and along the y direction would be P3 dl sin theta, right? And once we do the force balance along the x direction, we get that P1 dl cos theta would be equal to P3 dl cos theta. So cos theta will be cancelled, dl will get cancelled, so we will have P1 is equal to P3. Okay. Similar analysis can also be done for the along the y direction, which will give you P2 is equal to P3. Okay. So let's go to the next question. Okay. So this is an interesting question, I guess. So we can discuss about it thoroughly. So it is given that consider the two-dimensional stress field as shown in the figure. The plane AA, that's basically this one, is cutting through the element at a 30-degree angle as shown. Okay, so this angle is 30 degree and this is the plane AA. Okay, and these are the stress components: sigma xx, sigma yy, then sigma yx, sigma xy, sigma ys, sigma xy. Okay, so and I guess the notation of, if you try to understand the notation of these stress components, it will again be the revision of what we have discussed throughout in this problem solving session. This is basically the sign convention or the notation of the stress tensor, of the components of the stress tensor. And if we look into it, say if we consider this to be the Cartesian coordinate system for this particular problem. Sorry. Okay, so since this plane is perpendicular to the direction of the component or stress we are trying to evaluate or write, so this first index would be x, right? So it would be x, and the second is the direction that we are trying to along which we are trying to evaluate the force corresponding to this particular stress component is again along the x direction, so it will be sigma xx. Similarly, this would be since the plane along which we are trying to evaluate the force remains the same, so it will remain, the first index will remain x, but since direction of the evaluation of the force corresponding to this particular stress element has changed, so it will be now sigma x y. So similar analysis could be done for all other components. So I think it would be much simpler, or it would be a good exercise to understand the notations of the stress components in this question, so that what we've discussed throughout this session is, it will be revision for all of you, right? Okay. So the first question is that determine the magnitude of the shear stress acting on the plane A. It is given that sigma xx is 3000 Newton per meter square, sigma yy is 2000 Newton per meter square, and sigma xy is 500 Newton per meter square. Okay. So again, in these scenarios, it is quite it's quite it's quite a general practice to resort to force balance, assuming that the net force along the net shear force along that plane is 0, because it is not mentioned there's any deformation due to the shear force, so we can assume that the system is in equilibrium. So net shear so the net force due to the shear stress acting on that particular this particular plane is 0. Okay, so we can do the force balance here, and let us just go we can do the force balance there and then find the net shear stress that acts on the plane A. Okay, see, I'm not telling that the net shear stress is 0. What I'm trying to imply is that the net force due to the net shear net shear force that acts on the particular this particular plane is 0, because there is no deformation of the element because of the application of the shear stresses, right? That's why we can do a force balance, because the system is in equilibrium. Okay, so given that, we can do the force balance, the shear force the force balance in that particular element. So let me just go back to the derivations. Okay, sorry for the, okay, just zoom out a bit. Yes, so once we do the force balance, so this is the diagram. This is just simplified view of the diagram. So we have just denoted all the, oh, I'm sorry, so we have denoted all the values of the shear stresses that has been mentioned in the question. So we denote them here and do the force balance. Okay, so I suggest that you look to the force balance. So if there's any doubt, you can ask me. But I guess it's quite clear. But if you have any doubt, you can just ask me. Okay. So okay. So what we've ideally done is that since our plane is inclined at an angle of 30°, what we have done is we basically formed a two different axes that comprises or that indicates the net shear stress and the normal stress. Okay, or you can consider it, this to be the shear plane and normal plane. Okay, so if we consider this, like this is the plane that we are concerned, which is inclined at an angle of 30°. So we consider a different axis or different direction along which we want to balance our forces. Okay, see again, it is the forces that we balance, not the shear. Okay, sometimes people get there's a very silly mistake that people do, that they dissociate, or sorry, decompose the pressure component or stress component, but it's not the general practice. It's actually the force component, that force that we want to decompose in different directions. Okay, so if we create a coordinate axis where the line, where the axis along the surface of the this plane A denotes the shear plane, and the axis perpendicular to this plane A denotes the normal plane. Okay, so it is given that there is no deformation on this particular element because of either shear stress or the normal stress. Okay, so we can consider that both the shears, both the deform okay, so we are discussing a problem that will help you to solve the assignment questions for the first week. So let me just go back. So we're discussing this question. Okay, so I hope it is quite clearly visible. Okay, so the question is that consider a two-dimensional stress field as shown in the figure. Okay, the plane AA is cutting through the element at an angle of 30°. Okay, so this is the diagram that we are considering. So I hope it's quite clear now. The image is clear. So the question is that determine the magnitude of shear stress acting on the plane AA. Okay, so we need to determine the magnitude of shear stress that acts on this element AA. Okay, and it's given that sigma xs is 3000 Newton per meter square, sigma yy is 2000 Newton per meter square, and sigma xy is 500 Newton per meter square. Okay, and these are the corresponding stress component that is being shown in the figure. Okay, so in order to solve this, we have taken the help of force balance. So that is what I was discussing in the different diagram. So this is what we are doing here. So this is the particular wedge element that we are considering here, which comprises the plane of our concern. This plane AA. So since it is not mentioned in the question that the body is going any kind of deformation, so we'll take that the net deformation in the body is 0. So that's why the both the normal component of the force and the and the shear component of the force on this particular wedge element would be 0. Okay, the net normal force and the net shear force on this particular wedge element would be 0. Okay, not the shear stress but the shear force. Okay, that will be balanced. Okay, so so what we do is now what we do now is we do the shear stress shear force balance along the shear stress axis, right, that we have mentioned here, this axis. Okay, so if we do that, we find that we just do the force balance, so we can just write that. And if this has a length of L, then tau aa into L, which is x along the positive direction of the shear plane. Okay, I guess it will be quite difficult to go to each and every term, so it basically okay, let me just go to the first derivation. Okay, it will be quite helpful. So it is along the positive direction. Okay, now this component of, say, if we consider this plane now, say plane A, B, say. Okay, so in this particular surface there are two stresses, right? Stress, there is 3000 Newton per meter square and 500 Newton per meter square. Okay, so so then the net stresses that acts along uh, the tau aa axis would be, if we dissociate these stresses, then it would be 3000 Newton per meter square. Then it would be, this component would be, see, if it is 30 degree, and it will also be 30 degree, right? So this would be 3000 cos 30, and this would be 3000 sin 30, right? Similarly, this would be 500 cos 30, and it would be 500 sin 30. Okay, and since we need to balance the forces now, so we need to take into account the uh, surface along which these are acting, and this would basically be this surface, I'm sorry, this surface, so it is L1 sin 30, L sin 30. Okay, so basically we have done basically that. So 3000 cos 30 acts along the negative direction, so it has a minus sign here. Again, this one with respect to, if we consider, if we cancel out the minus sign, then this is along the positive tau aa direction, so it would be plus 500 sin 30 into L sin 30 degree. Okay, so this we should not forget. Okay, so similar could be done for this plane, BA plane. So do the same dissociation, same decomposition, and then finally if we just balance this forces, we will get that tau aa is equal to 683 Newton per meter square. Okay, so that would give us the option, to go back to the question, so option D. Okay, so option D would be the correct answer. Okay, similarly the next question is again, determine the magnitude of normal stress acting on the plane A. Same, the stress the values of the magnitudes of the stresses are same. So you can directly go back to the same diagram. Okay, I guess it is difficult, so I will just, let me just copy it, so it will be simpler. So copy and just say paste it here, if it is okay. So okay, a smaller version. Okay, so we do the same thing, so we do the same force balance again along along the normal, in the direction of the normal plane. Okay, so we'll do the same analysis. So sigma A into L again, it will be 3000 sine 30, that was this component plus 500 cos 30, this along this component, into L sine 30 degree. Okay, this plane measured with respect to this length. Okay, similarly for this components of stress as well. So once we do that, we get that sigma A is equal to 2683 Newton per meter square. Okay. Okay, so the answer, if we go back to the options, we get that the right answer would be option A. Okay. Now, I just wanted to introduce you, solve this question using a different approach. Okay. So, if we go back to this diagram, and this question in general, uh, these kinds of analysis are again this finding the forces, net normal force and shear force in a particular element are are done extensively while evaluating in the case of solid mechanics as well. Okay, so there the people use the concept of more circle to determine the value of these stress components, but again there are some analytical approaches as well to determine this shear and normal components of the stress on a particular plane that is inclined at a particular certain degree. Okay, so using that using that approach, so using that concept, we find that we can use this formula to find the stress component. Okay, the component of the uh, shear stress. Okay, so this is the formula. So you can, if you want, you can just remember or take a screenshot. It's completely fine. It's just a formula that this is being used while in the case of solid mechanics. So I found that this applicable for this kind of scenarios as well. So we can just use that. But in this case, just for our ease of understanding, we have taken the angle to be 60 degree. Angle of for our consideration is 60 degree, because since it is 30 degree and this is normal, so this would be 60 degree, right? So keeping that in mind, our theta for our analysis that we are using in the say in the consider more circle, it is 60 degree. Okay, and you know how the 60 degree came right here, right? So the normal component of the shear stress is given by tau xy or sigma xy in this case, that indicates the shear stress that acts along the surfaces of the element. So tau xy cos 2 theta minus 1 by 2 sigma x minus sigma y sine 2 theta, and this sigma x and sigma y denotes the normal components of the stress that acts along the surface of the element. Okay, not the inclined surface, but the outer surfaces of the element. Okay, so once we substitute those values, the tau xy is equal to 500 Newton per meter square, cos 120 degree, because theta is 60, as I told how it came, and into minus half 3000 minus 2000 into sine 120 again. Okay, theta is 60, so it will be 120. So once we evaluate that, you get that tau n is equal to minus 683 Newton per meter square. Okay, so see, in the case of stress, at least these minus and positive signs are basically just tells, at least in the case of shear stress, it indicates that these are just the uh, stress acting in the opposite direction of what we are stress acting along the in the opposite sense of what we are assuming the stress to act. Okay, so uh, we know that from the principle of say a principle of complementary shear stresses. So uh, in order for a system to be in equilibrium, there would be an shear stress that will have to act along in a direction positive, in a direction opposite to this direction of shear stress, to maintain the equilibrium and thus generate the complementary shear stresses. Okay, so this basically what I'm trying to say is this: if you go look into this diagram, so if there is a sigma yx acting along this direction, there is a corresponding sigma yx that acts in the opposite phase, so that it could balance, or it could
Okay, I'm sorry. So if sigma yx is acting along this direction, there is a stress component at x in the opposite phase that is in the opposite direction of the sigma yx in this phase, and this opposing nature or opposing sense of the shear stresses would generate complementary shear stresses, sigma xy in this plane and sigma xy in this plane, that would uh, prevent the body from going a shear deformation, body from undergoing a shear deformation. Okay, so this is what the concept or principle of complementary shear stresses. So wherever there is a particular shear stress along a certain plane, in order to have that body not undergo any shear deformation, there would be there would be a corresponding shear stress, say in the opposite surface of the particular element, that would be generated in the opposite direction, that would in turn result in the generation of complementary shear stresses that would in turn prevent the shear deformation of the uh, particular element. Okay, so keeping that in mind, see, so only the magnitude, sorry, only the the sign is different, but the magnitude is exactly the same as what we have obtained from our force balance. Okay, similarly, if we apply the same Mohr circle concept in the evaluation of the normal stresses, we find that we can use the same concept here. Theta would be 60 degree, and the formula for finding a normal stress would be sigma n would be equal to half sigma x plus sigma y plus half sigma x minus sigma y cos 2 theta plus tau xy sin theta. Okay, sigma x and sigma y are equal to sigma xs and sigma sigma yy in our given diagram, and tau xy is equal to sigma xy. Just substitute the value of the given stresses, then we find that sigma n would be equal to 2680 Newton per meter square. It is exactly the same as what we have obtained here. Okay, so these are just two different approaches or ways to find the same solution, but I found it interesting that we could apply the same concept here. Obviously we can apply it, but just wanted you to all to know. Okay, so now we go to question number 10. So again, this is simple force balance. Okay, so we are asked to determine the shear stress sigma xy, given that sigma xs is equal to 2000 Newton per meter square, sigma yy is 3000 Newton per meter square, and sigma n, the normal stress along the plane A, is 2500 Newton per meter square. Okay, so basically now we just need to do the force balance, the same force balance that we have done in the previous case, and just substitute these values in our force balance and find the unknown sigma xy. Okay, so it's quite simple, but still you just need to look at the steps. Then again, just do a simple force balance. The only unknown would be here, the sigma would be the sigma xy. Just substitute the values of the given stresses here. See, the value of normal stresses have been changed here now. Basically they are interchanged actually, but you need to look into it. Okay, don't skip it. So sigma xs is 2000, just substitute the value here. Sigma y is 3000, and sigma n is 2500 Newton per meter square. Just substitute the value here, and we get that sigma xy would be equal to minus 289 Newton per meter square. Okay, and similarly, okay, let me just go back. So right answer would be B. Okay. And you may ask, like, but the what we're getting is minus, but we are again option is B, option B, where there is no minus sign. But see, they've asked explicitly the magnitude of shear stress. Okay, and as I told that this would just mean that there is an opposing stress in the opposite sense in the different the opposite face of the same element, so there's no point of again uh, just getting confused. So they're just asking the magnitude of the shear stress. Okay, so it is 289. Okay, and final question is again, oh, it's way below. Okay, so determine the shear stress on the plane A given that. Okay, I guess I have repeated the question, so I'm sorry. So the questions are repeating, so you can just okay, let me just go. I'm sorry. Okay, the question is repeated in this PDF, but we can just uh, correct it. Okay, so okay, okay. So now they're asking that determine the magnitude of shear stress on plane. I am sorry, I was just confused with sigma xy and shear stress. So they're asking that determine the magnitude of shear stress on plane AA. Okay, so basically we need to find tau AA. Okay, the shear stress on the plane AA. Given that sigma xx is 2000 Newton per meter square, sigma yy is 3000 Newton per meter square, and sigma n is equal to 2500 Newton per meter square. See, the trick is here that now for determine the shear stress on the plane A in the force balance, we do not need sigma and AA. Okay, but the trick is that since we already know that sigma and AA would give us to a corresponding shear stress of a magnitude of 289 Newton per meter square that we got from our previous analysis, we can just plug in the value of the shear stress, this minus in this case now, of the shear stress in our force balance, and then evaluate tau A. Okay, so it's quite simple. Again, just substitute the value of, if you look into here, just substitute the value of sigma xy0 289 as I mentioned just now. Sigma xy0 minus 289 into per meter square in the force balance for when we are trying to determine tau A, then we can finally get that tau A is equal to minus 577 Newton per meter square. So that would be again option C. Okay. Okay, so I feel that's all for today's class. uh, I hope it would be quite these problems would be quite helpful for your understanding of the concepts, as well as help you to solve the problems for the first week of the introduction to fluid mechanics course. So I hope it will be quite helpful for all of you, and if you have any doubt, you can just put those your doubts in the discussion forum of the course website, or just ask, you can write those doubts and just ask me in the next session, that is in the coming Friday. Okay, so there are other two sessions from the other two TAs as well, so I insist that you join those sessions as well. That will be quite helpful. And again, if you have any doubt regarding the concepts, you can just go back and attend and revisit the lectures by Professor Chakraborty. That would be very helpful. And I guess that's all from today. That's all from my side for today. And thank you. And that's all. Thank you.